Often we don't notice it's even there, but it's all around us. It's in our environment, it's in our water, it's in our homes, our streets, and our food. It is at the center of new technology, new forms of energy, new ways to fight disease, and new ways to solve the problems we all face together. It is every day, and it is life-changing. It is the future.
Right. Hello. Yeah, I hope you can hear me. All right. Can you hear me? Everyone? Yes. So, okay. Right. Let's begin. Let's begin our discussion. Right. Let's start here. So I hope you have the paper as well. That is the paper number 12. Clear? Can you see the screen? Everyone? Yeah. Can you? Yes. Okay. Okay. Right. Let us start. Right. Let us start. 20, paper number 12, question number 1, right? Okay. So first one, question number 1 here. It says, which of the following is the most suitable Lewis structure for CNO, right? CNO. right? So if you look at CnO minus, what would be the central atom? What is the most likely the central atom? Right? Carbon is the central atom. Why? Because it has a kind of a higher valency, right? So let us look at the electrons, number of electrons. Carbon gives you 4, and then nitrogen gives you 5 electrons, and oxygen gives you how many electrons? How many electrons? 6 electrons. And because of the negative charge, 1. So 4, 5, 9, 1 electron here. Because of the negative charge, 10, altogether 16 electrons. Divide by 2, 8 pairs. 8 pairs. And then we keep carbon in the center, nitrogen on one side, and oxygen on the other side. So out of that, you have used 2 bond pairs. That means 6 electrons that are remaining. So these 6 electrons, 1, 2, 3, 4, no, we'll start with oxygen. 1, 2, 3, 4, 5, and 6. Is it clear? Let us look at the charges. Oxygen, how many? 1, 2, 3, 4, 5, 6, 7, minus 1. Minus 1 is the charge. Carbon, 1, 2, that means it has plus 2. What is the charge on nitrogen? 1, 2, 3, 4, 5, 6, 7. Minus 2. Is it clear? Right? So which side do we want to minimize? You can keep the negative side, negative charge on oxygen. Nitrogen is less electronegative. So therefore, you can bring the electrons to this side. And you can get oxygen, carbon, triple bond nitrogen. And this is the lone pair, right? And this one, 1, 2, 3, 4, 5, 6, negative. I think that is the best structure. That is the best structure that you have, right? So which one is that? Can you suggest an answer? Yes, yes, everybody, right? Now don't waste any time. Your exam is scheduled for October for the moment, at the moment, right? So immediately take some, do your work and finish it up, right? Second answer, right? Good, excellent. Right, let's go to the second one. Second question is this. The concentration of an aqueous solution of methanol is 10% by weight. So methanol is CH3OH. CH3OH, you have 10%. 10 grams. What is the other one? Aqueous solution. So other part is water. So how many grams? 90 grams there. Right? If the relative atomic masses carbon, hydrogen, 12, 1, and 16, the molar fraction of methanol in this solution is, right? Let us calculate the number of moles here. 10 divided by, what is the molecular mass of methanol? 12 plus 4 plus 16. What is that? 32 is the molecular mass. What is the molecular mass here? 90 divided by 18. What is that answer? 10 divided by 32. 10 divided by 32 is equal to 0.3125. 3125 moles. Here, 90 divided by 18 is 5 moles. So what is the molar fraction? Molar fraction of methanol is 0.3125 divided by 5.3125. What is the answer? Divide by 5.3125. 0.0588, fourth answer. 0.0588 is your fourth answer. Is it clear? Did you understand that? Did you get the answer, children? Right, very good. Question number 3. Let's read that question. We'll work it out. Question number 3 here. When the temperature of an ideal gas is reduced by keeping the volume at a constant value, the pressure of the gas decreases. The pressure of the gas decreases. What can be the reason for that? What can be the reason for that? Increasing intermolecular attraction of molecules, right? Now, if it is an ideal gas, no intermolecular forces present. So therefore, that is wrong. Huh? Decrease in the number of collisions per unit time between gas particles. Of course, the number of collisions per unit time decreases. Between gas particles also decreases, but that is not what pressure is. Pressure is when it is colliding on the wall of the container. So B is wrong. Decrease in the velocity of gas molecules and collisions of the particles with the wall of the container. I think that is right. C is a right statement, right? Increasing the distance between gas particles and low temperature collisions are not perfectly elastic. So C, D and E are not the answers. This one is the answer. So you need to make sure that the collisions on the wall of the container. Is it clear? Right? Then the fourth one, we'll work out the next one. What is the molarity of barium hydroxide solution if 35 milliliters of 0.1 mole HCl is used in the titration of 25 milliliters of barium hydroxide? What is the first thing that we do? We write the reaction, barium hydroxide and then HCl. What do you get? What are the products that you get? Barium what? Barium chloride plus water. So how does the reaction work? This is 2HCl and this is 2 water as well. So stoichiometry, barium hydroxide and then HCl, number of moles of HCl. Stoichiometry is 1:2. Now I think you can substitute. What is the molarity of barium hydroxide solution if 35 milliliters of 0.1 mole HCl? So 35 milliliters concentration is 0.1 molar. Is used to titration 25 milliliters. 25 milliliters, what is the molarity? Molarity is the concentration, is equal to 1:2. So there are certain things that will cancel out. Milliliters cancels out. And concentration is equal to 0.1 times 35 divided by 25 times 2, 50. What is the unit? Moles per cubic decimeter. Check whether you have an answer there. 0.1 times 35 divided by 50 is your answer. 0.07 moles is the answer. What is the answer? Fourth one, first answer. Is it clear? Everybody got that answer? What do you think? Everyone? Right. Okay. Question number 5. Right. Question number 5. Read that question, will you? A solution of ferrous chloride with a concentration C and volume V needed 30 milliliters of acidic potassium permanganate with the concentration C2 for complete oxidation. Calculate the volume of dichromate with concentration C2 needed for the complete oxidation of FeCl2 solution with the same volume V and C. Right. Now, one is ferrous chloride with potassium permanganate. The other one is ferrous chloride with potassium dichromate. So we need to balance the reaction. Now, assume that chloride doesn't react. Assuming that chloride is not reactive with this potassium permanganate, we'll see how the reaction actually works. Right. So chloride not reactive. Okay. So what would happen is you have Fe plus 2 MnO4 minus giving you Fe plus 3. MnO4 minus turns into Mn plus 2. Right? That's the reaction that we are going to look at. So this is plus 2. This is plus 3. You see 1 electron participated in that reaction. This is +7. This is +2. How many electrons? You see 5 electrons participating in that reaction. Right? Balance it. Now you don't have to balance it. Like when you're doing the MCQ, you don't have to balance it. You can, of course, say this is 5 electrons, this is 1 electron. You have to multiply this by 5. So you write 5 here and 1 here. Stoichiometry is 5:1. Right? But then I think it is better to balance and practice those. 5 here. This is 1 potassium permanganate, 4 H2O here, and then you get 8H plus also on this side. You don't need them. You need only the stoichiometry, right? Is it clear? Right? So, number of moles of Fe+2 divided by number of moles of potassium permanganate. What is that? Number of moles of Fe+2 is 5. Number of moles of potassium permanganate is 1. Did you understand that? So Fe+2, let us say concentration C and volume V. So I say concentration C, volume V divided by needed 30 milliliters of acidic potassium permanganate with a concentration C2. C2 times 30 is equal to 5 divided by 1. Right? So I can say CV is equal to 150 C2 using the first equation. Did you understand that? Did you understand that? CV is equal 150 C2. Everybody understood that? No, they can. You all got the idea there. So you get this relationship between CV. And then it says, calculate the volume of dichromate with concentration C2 needed to completely oxidize FeCl2. So we now let us look at how Fe+2 react with potassium dichromate. Fe+2 dichromate Cr2O7 2-. Gives you Cr+3. And then that will give you Mn+2. Right? Fe+2 turns into Fe+2 also turns into Fe+3. Right? Fe+3. It turns into Fe+3. Right? So this is turning into that. Not Mn+2. Right? No Mn+2. Let me erase that. Right. Okay. So there you have. It turns into Fe+3. Fe+2 turns into Fe+3, right? So that is 1 electron. That gives you 1 electron. This one is +6, goes to +3. How many electrons is that? 3 electrons, because there are 2 atoms, you have 6 electrons. So now you can, what you can do is you have to multiply this by 6. So you get 6 here, 6 here, this is 2, and this would be 1, right? Right. So number of moles of Fe+2 to number of moles of dichromate. What is the value? What is the stoichiometry? 6:1. 6:1. So what is the number of moles of Fe+2 present? C and V. C times V. What is the concentration of dichromate C2? What is the volume? V, let us say V1 here. V1 is equal to 6:1. But then we know CV is equal 150 C2 using the earlier equation here. Look at this one. CV is equal to 150 C2. So based on that, we can calculate CV is equal to 150 C2 divided by C2 V1 is equal to 6 to 1. C2 cancels out. What is V1? V1 is equal to 150 divided by 6. බලන්න උත්තරයක් තියෙනවද කියලා? Is their answer? 150 divided by 6 is equal to, what is the answer? You get 25 milliliters. Did you understand that? What is the answer? Second answer is the right answer. Did you get that answer, children? What do you say? Did you get that answer? That is I think that is a little bit of a tough question. You have to balance, like, kind of two equations and get the value there. Is it clear? Everybody? Right. Very good. Well done. Okay. So question number 6 here. Now this comes from energetics. This is the first time we are 250 milliliters of 0.5 molar potassium hydroxide at 29 degrees Celsius. Right? You have 250 milliliters. 0.5 molar KOH. (29 degrees Celsius). 29 degrees Celsius was neutralized with equal volume. That means you have to add 250 milliliters of HCl, some amount of HCl, and the temperature was 32.4. It goes to 32.4 degrees Celsius. What is the enthalpy change of neutralization for the reaction? Heat capacity of the mixture and the polystyrene cup is 2.1. Heat capacity is 2.1. So how do you calculate that? The energy Q is equal to, what is that? MC theta. Heat capacity means this entire part. MC product together is heat capacity. So I say Cp theta. So what is the Cp value? Cp value is given as 2.1 kilojoules per Kelvin. Kilojoules per Kelvin. This entire content, water, whatever the solution that is there, polystyrene cup, everything together, it has a heat capacity of kilojoules per Kelvin. And what is the temperature change? Temperature change is equal to 32.4 minus 29. This is given in Celsius, but it is also equal to the same amount in Kelvin. I told you temperature change in Celsius and Kelvin both are the same, right? You should not add anything. 32.4 minus 29 gives you some value multiplied by 2.1 is equal to 7.14. 7.14 kilojoules. You agree with that? 7.14 kilojoules is needed, right? Now let us look at the number of moles of potassium hydroxide added. What is the number of moles of potassium hydroxide added to this? 0.5 250 milliliters. 0.5 times 250 10 to the power minus 3. What is that number of moles? What is that number of moles? 0.5 times 250 10 to the power minus 3 is equal to point. What is the answer? Point. Very quickly. 125 moles. So this is for 1.125 moles to neutralize. So what is the enthalpy change? Enthalpy change is given for 1 mole. For 1 mole. How much is that? This is temperature is gone up. That means it is exothermic. Energy is given out. So therefore we write it as minus exothermic. How do you know it is exothermic? Because the temperature goes up. Right? From 29 to 32.5. Temperature goes up. 7.14 kilojoules. for how many moles? 0.125 moles. So what is that value? 7.14 divided by 0.125 is equal to 57.12. So our answer is minus 57.12 kilojoules per moles. Agree with that? Did you understand that fully? Fully, right? The tutorial that I gave you last week, like in initial parts, the energetic question, they are full of these different types of questions. You should be able to do them. Right? Clear? Is it clear now? Everybody understood that? 57.12 is your answer. Energy is given out. No, you can't do it like that. Somebody says the reaction taking place between a strong base and a strong acid, also it is a neutralization. But then, you have to do the calculation and then say, we don't know. If it is sulfuric, how do you know? It's not sulfuric, but then you need to do the calculation and get it, right? It's good that you get the same answer, right? Is it clear? Okay. Now the next one is this. Question number 7. Right. Read the question and see whether how this is going to go. How is MC? MC means this. MC means heat capacity. This is specific heat capacity. No, C means specific heat capacity. This one is specific. Heat capacity. So combined with mass, it is called heat capacity. MC is heat capacity. Right. Question number 7. Which of the following statements are true regarding a gas? First one. Regarding a gas, regarding the gas. The total mass of an ideal gas is negligible. What can you say? Again. Now, y'all tell me. Again. Give me some answers. What do you think? Total mass of an ideal gas is negligible. What do you think? No. Yes, it's a false statement. Why? You can't have this matter. Matter must have some kind of a mass. That is wrong, right? B, the volume of an ideal gas at constant pressure doubles when the temperature is raised from 300 to 400. 300 to 400, the volume doubles, it says. No, P1 V1 divided by T1 is equal to P2 V2 divided by T2. Right? Constant pressure. So pressure and pressure cancels out. So you can say V1 divided by 300 Kelvin is equal to V2 divided by 400 Kelvin. So what is V2? V2 is equal to 4 divided by 3 V1. So that is not doubled. So that is also false. Right, good. Then the third one, what can you say? The compressibility coefficient is used to measure the deviation of a real gas from the ideal gas. What can you say? I think that is a true statement. You remember, we plot pressure versus compressibility factor. Compressibility factor, PV divided by nRT. Z is equal to 1. Z is equal to 1 for a ideal gas, right there. But then you have these kinds of gases like that. There can be like deviations there. These are non-ideal gases. So these are non-ideal and this is an ideal gas. Right? This is an ideal gas. So I think C is a right statement. That is not a problem. Conditions where ideal behavior can be expected from the real gases are very low pressures and high temperatures. What can you say about that? D is also correct. At very low pressures and very high temperatures, the volume is high. So now the particles are like, far away from each other, independent from each other, so they can behave as ideal gases, right? They are acting like point masses, so you have a high volume. So D is right. A, B, B, C, C, D. C, D is which answer? I think third answer is the right answer. Agree with that? Everybody? Right. Good. Question number 8. Think about that. Which of the following statements pertaining to the composition of the solution prepared dissolving 18 grams of glucose? 18 grams of glucose, 18 grams of C6H12O6 glucose together with 180 grams of water. 180 grams of water, right? At 277 is our true. Okay, one density of this one. So first one, it says concentration of glucose in the solution is 0.55 moles per cubic decimeter. What can you say about that? What can you say about that? Concentration is 0.55. Let us calculate the number of moles of glucose. Number of moles of glucose is 18 divided by 180. So 0.1. What would be the volume? What would be the volume? There is the number of moles of glucose. What is the volume? Volume is what? 100, because the density is 1 gram per cubic centimeter, 180 milliliters. But when you add these two together, do you know the final volume? Do you know the final volume? Yes or no? Ko ala, right? Do you know the final volume? You don't know the final volume, right? You have water 180 milliliters and you add glucose 18 grams to it. And the volume changes now. Total volume is not you don't know the final volume. So if you don't know the final volume, you can't calculate the concentration. So therefore, you can't calculate the concentration. Right? So isn't a volume of 18 grams of glucose is negligible? You see, it is not negligible. How can you say it is negligible? Right? Did you understand that? You can't say it is not negligible. You can't, even if you, if it is 18 grams, that's quite a lot. And then, even if it is that, I told you, in my note, I have given you, if somebody says you are adding this milliliters and then you are dissolving it, you can't calculate the concentration at all, right? Because you have a 118 milliliters of water and then you are adding 18 grams to it. Of course, the volume increases and you don't know the final volume. So the concentration of glucose in the solution is this much. That is wrong, right? A is a wrong statement. Why? Because the final volume is not known. Did you understand that? Is it clear? Because if you add something into existing volume, of course the volume goes up, right? Okay. So then the second one, B, the mass fraction. In the mass fraction. So mass fraction, what is mass fraction? Mass fraction is the mass of glucose 18 divided by the total mass 180 80 plus 18. That is the mass fraction. So what is that value? 18 divided by 180 plus 18. Right? 0.090. 0.090. 0.090. So what they have given is the mass fraction of glucose in the solution is 0.1. That is a wrong statement. Mass fraction is wrong there, right? B. C. The molality of glucose in the solution is 0.1 moles per kilogram, right? So what is molality? Molality is equal to number of moles of glucose divided by the mass of the solvent, right? Mass of the solvent. Number of moles of glucose is how much? 18 divided by 180. This is the number of moles. What is the mass of the solvent? Mass of the solvent is 180. So 180, 10 to the power minus 3 kilograms. Right? So what is that answer? 18 divided by 180 divide by 180 10 to the power minus 3 is equal to 0.555. 0.55 moles per kilogram. So that is also a wrong statement. Is it clear? Right? Did you understand that? Okay. The mole fraction of glucose in the solution is 1 divided by 101. CD. Right. Let us look at the mole fraction. Number of moles of glucose is equal to 18 divided by molecular mass 180. What is that? 0.1. Number of moles of water is equal to how many grams? 180 divided by 18, that is 10. So molar fraction of glucose is equal to 0.1 divided by 10 plus 0.1. 0.1 divided by 10.1 is equal to 1 divided by 101. I think that is a right statement, right? Clear? Right? So that is a right statement. So therefore, 5. Answer 5 is the right answer. Only D is right. Is it clear? Did you understand that? Answer number 5. Everybody okay with that? So fifth statement is correct. Correct statement. Huh? Correct statement. Everybody okay with that? Why B is wrong? Why do you think that B is right? That is wrong. Why B is wrong, you ask? The mass fraction of glucose in the solution is 0.1 is the statement. Look at the mass fraction. Mass fraction is 18 divided by 198. That is not 0.1. That is 0.09. It's not 0.1. Right, okay. So question number 9. Right, see whether this is okay. What do you think? Ideal gas cannot be liquefied at high pressure by lowering the temperature. Huh? Ideal gas cannot be liquefied at high pressure by lowering the temperature. What do you think? That's a correct statement. Ideal gases have no interactions, no intermolecular forces, no IMF, intermolecular forces. So cannot be liquefied. Yes, right? Cannot be liquefied at any cost, right? So that's a right statement. When a real gas is above its critical temperature, it can be liquefied by compressing. Critical temperature is the point where you get the maximum temperature of which the liquid vapor equilibrium exists. Liquid vapor equilibrium exists. Above that temperature, you can't increase the pressure and liquidize, right? This is the very last part of gas, right? So that is a wrong statement. Wrong statement. If you want, you can write down there. Critical temperature is the maximum temperature where the liquid vapor equilibrium exists. Any temperature above that does not favor this equilibrium. Does not favor that equilibrium. This is the maximum temperature. Critical temperature is that. So if you look at this point here, this is the temperature, this is the pressure. We drew this kind of graph like that. Okay. So this is called the solid phase. This is the liquid phase and this is the gas phase. So this part is called the triple point. Triple point is the point where the temperature, the solid, liquid, gas, everything exists at equilibrium. Right? Solid, liquid, gas, everything exists at equilibrium. If you look at this point here, this point that we talk about here, that is what is called the critical point. This is the maximum temperature. You can see here, this gives you the maximum temperature. This is that maximum temperature, right? Maximum temperature where the liquid vapor equilibrium exists. Beyond that point, you don't see any liquid vapor equilibrium. This is the point. Beyond that point, you don't see any liquid vapor equilibrium exist. So this is what I said. This is the maximum temperature of which liquid vapor equilibrium exists. Beyond that temperature, how much you try, you can't increase the pressure and liquidize it. That is what is called critical. Limiting stage. So after that point, it will be, you can't do it. That is why it is called critical temperature. Critical temperature is the point where the liquid can be turned into a gas, or gas can be turned into a liquid by increasing the pressure. Right? Did you understand that? So that is a wrong statement. Huh? Right. Then we will move on to the very last part. Question number 10. The hardness of diamond is very much higher than the hardness of solid carbon dioxide. Hardness of diamond is very much higher than the hardness of solid carbon dioxide. I think that is right. Right? Carbon, like, diamond, what you have is covalent bonds. Carbon dioxide, what you have is London dispersion forces. Their hardness is very much less. Higher hardness because of its tetrahedral nature. The carbon-carbon bond strength is very much higher than the carbon-oxygen bond strength. What can you say? Carbon-carbon bond strength is very much higher than carbon-oxygen bond strength. Is it a true statement or a false statement? Yeah. Carbon-carbon bond strength is very much higher. That is a false statement. Why? Carbon-carbon is a single bond. Carbon-oxygen is a double bond here. Double bonds are double bond. If you are going to break that, you have to break the pi bond and the sigma bond both together. So carbon-oxygen bond is stronger compared to a single carbon-carbon bond. right? So that's a is it agreeable to you? Is it agreeable to you? Right? So this is true and the other one is false, right? So true and false is the third answer. Somebody asked me carbon-carbon bond is stronger than carbon-oxygen bond. Carbon-carbon double bond is stronger than carbon-oxygen bond. Yes, carbon-oxygen bond is polarized. Carbon-carbon single bond is not polarized. So therefore, double bond is stronger. What do you mean by why? Why? When you say why, for what are we talking about why? Are we talking about how means why, how, all these things, you need to complete the sentence. This is just a word of a sentence. What do you mean by how, what? Because of polar, non-polar bond? I don't understand what you're asking here. What do you mean why and how is like the carbon-carbon double bond stronger or carbon-carbon single bond is weaker? What are we asking here? Oh, bond strength is mainly found by bond order. Yeah, bond order you can use if you are comparing similar bonds. In this case, it is the double bond or a single bond. How come carbon-carbon double bond is stronger? Carbon-carbon double bond is stronger than carbon-oxygen double bond, right? Carbon-carbon. Now here, like, understand the second statement. This is a carbon-carbon single bond. Carbon-carbon single bond strength is very much higher than the carbon-oxygen bond double bond strength. Carbon-oxygen double bond, you have a pi bond and a sigma bond. Here is just a sigma bond, that's all, right? So there's a additional pi bond strength. So breaking a double bond completely is difficult. So that is why we say carbon-carbon double bond. Is it clear? If you, what is that? Is the second statement is not connected with the first statement? It's not connected, it's anyway wrong, right? So diamond has a, not a, it's a homoatomic giant covalent lattice that is there. The other one is a molecular lattice. Molecules are held together by London dispersion forces. They are very weak. Did you understand that? Can you please explain the first statement again? The hardness of diamond is the most hardest material, naturally found hardest material on earth. Carbon dioxide is not that hard, right? Okay, right. Right. So what is the other one? It says carbon, especially in diamond network structure, are generally much stronger than carbon-oxygen bond in CO2 or other molecules. Yeah, any carbon-carbon bond, because network structure becomes stronger. It requires higher melting point, melting temperature, because of the large number of bonds that are present. Carbon-oxygen, in carbon dioxide, we are not breaking carbon-oxygen bonds. We are breaking the London dispersion forces between CO2. So that is anyway much weaker interactions. Can we say there are sp3 and sp hybridization? Of course there are, yes. But that doesn't affect here, right? Can I know the answer for the ninth question? Ninth question is the third answer. Answer number 3. Answer number 3 here. True and false. True and false. Answer number 3. Other one is also answer number 3. And somebody asked me something else. What is that? Question number? Which question is that? Tell me the answers for the first and the second question. Yes. First and the second question. Ninth question. But question number 9 is answer. Right? So when you do things, you become better at it, right? Better than when we started. Have you ever noticed that? You make less mistakes, you are thinking better, and you have a better way of looking at it, right? Clear? That's good. So this is related to the fifth question. In the acidic medium, does chromate also turns to, now chromate is not stable in acidic medium. Chromate turns into dichromate. That dichromate turns into Cr+3. Chromate doesn't exist in acidic medium. Chromate ions, right? When you explain part A, structured part first question, can you explain a little bit more detail, because I'm kind of confused in that area, right? Okay. So I'll try to explain, meaning this is, I told you, this is like a booster kind of thing, right? In order to like make it but beneficial for everyone, I'll try my best to explain whatever the material that is needed into this, right? You can't go out of that, because then others will feel bored. You know how this is, right? Very difficult to keep people's attention for a long period of time, right? Very, very difficult. You know that. But then just after finishing the discussion, if you wait and if you kind of budge me little stronger, I'm happy to stay and teach you, right? Right? Okay? I think that is fair enough for everyone, isn't it? Okay, right. Okay, good. I'm glad that we can agree on that. Arrange the given species in the ascending order of the property stated in the parentheses. So, ascending order means increasing order. So they have given rubidium, right? Sodium, lithium, potassium, and cesium. So they're talking about the melting point. Now, melting point for these ones, it depends on the strength of the metallic bond. So it depends on the strength of the metallic bond. Strength of metallic bond. Now, strength of the metallic bond depends on the number of electrons and the charge density. I will write that. Number of electrons and charge density. It depends on these two parameters. Is it clear? The number of electrons would be the same, because all of these elements belong to the group 1. All of these elements belong to the group 1. So therefore, number of electrons are the same. So it all depends on the charge density. Density depends on the charge divided by the radius, volume. Higher the volume, weaker the metallic bond. Did you understand that? So I want you to write it now. I don't want to mention the name, but then our friend who said part A, structured part first question, it is little difficult for me. What you can do is, this is how you improve it. Make improve. This is like at this moment, don't worry about the timing, all that. So, but make sure to write them in detail. Just write them in detail. Okay, you understand, kind of similar bunch of questions that is there, right? You can improve. Never too late. Okay, and you will be great. You can finish it really well. So you get a weaker metallic bond. Yeah. So like, maybe you might not be able to write it right now when I'm like telling you all this. And this video is also uploaded to the Sampath sir's website. So yeah, you can download that. You can rewatch free පොඩි වෙලාවක් අරගෙන and then write them down. එතකොට ඔක ඔහොම බලනකොට it will be okay, right? You have to kind of engage it with it, and little that you know, you will improve very well. Right. So you can see if you look at the lithium, sodium, potassium, rubidium, cesium. This is how elements are arranged in the periodic table. Keep that periodic table with you. It's always helpful, right? So down the group: lithium, sodium, potassium, rubidium, cesium. So cesium has the largest radius and lowest charge density. So cesium has the lowest melting point. Then have rubidium, then potassium, then sodium, and then lithium. Is your answer. Clear? Did you understand that? Everybody? Is it clear? Right? All of you got that, I hope. Second question is this. CH4 hydrogen sulfide ICl4 minus. CH4 hydrogen sulfide ICl4 minus. Right? ICl4 minus. Bond angle. CH4 is tetrahedral geometry. What is the bond angle? Can you tell me tetrahedral geometry? What is the bond angle? Right? 109.5. Right? Now somebody asked me how number of electrons affect the melting point. Higher the number of electrons, stronger the melting metallic bond. Lower the number of electrons, it is weaker the metallic bond. Weaker the metallic bond, you can break it easily. Right? So CH4 109.5. Hydrogen sulfide, you have sulfur like that. You have a hydrogen here. What is the bond angle? 109.5. That is the rough bond angle. Minus how many degrees do you deduct? Taggal again. Well, when that you like all මට කලින් උත්තර දීලා හිටියේ. Then now I think you can see, I can see that there's a මේ ටක් ගාලා පොඩි නිකන් තියෙනවා, like there's a මේ පොඩි interest එකේ drop එකක් වගේ තියෙනවා වගේ මට නිකන් හිතෙනවා එහෙම. I don't know, maybe you know and then you are too proud to share it with me. අර එහෙමත් තියෙනවනේ ටික කාලයක් යනකොට දන්නවා වැඩි වුණාවත් එහෙම වෙනවා. Right? Okay, so I wish you can share. ඔක share කරන තරමට තමයි joy එක තියෙන්නේ. Joy you get when you share it. හරිද? ඒකින්ද share කරන්න එහෙම ආඩම්බර වෙන්න එපා. ICl4 minus. What is the ICl4 minus? Iodine, Cl. There's a lone pair here. And there's a lone pair here. Right? I say dotted line here, right? Clear? And that is the minus charge. What is the bond angle? Square plane. What is the bond angle? 90 degrees. Right? So 90 degrees. Is it clear? Right. So what is the answer there? Bond angle increasing order. So we'll start with ICl4 minus is the lowest. Then what is the next one? H2S. What is the next one? CH4. Did you understand that? Is it clear? Right? What do you mean by no? What is no? What is no? Right. Is that clear to you? Did you get the answers? Anything? Yeah. Okay. So next one is the third one. Third one is this, first ionization energy, right? First ionization energy. What is this first ionization energy? I think, what I do is usually I plot the first ionization energies. How much it might take little bit of time, but then you can't buy hard this. So you need to kind of plot the ionization energy. Sodium, now lithium, this is nitrogen, oxygen is also there. Right. So this is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. And this one is sodium, magnesium, aluminium. So what are the elements that they ask? Aluminium, fluorine, nitrogen, oxygen, sodium. So we'll start with sodium. Lowest one is sodium. Increasing order, sodium. What is the next one? Aluminium. Right. Sodium, aluminium. What is the next one? They say sodium, aluminium, fluorine, oxygen, nitrogen. So what is the highest one is fluorine, I think. Oxygen is the next one. Then nitrogen, then fluorine. What do you think? Think about that answer. Because again, you agree with that answer. Right? Is it clear? Right. Okay, good. I wanted to know only the boiling point in there. So I didn't get it now. I didn't get it now. Okay, right, fine. Next one is this fourth one. Somebody says ICl minus. Can you explain ICl minus? ICl minus, this is how you usually work it out. ICl minus, iodine 7 electrons. Chlorine also 7 electrons. 7 times 4, 28. 7 times 4, 28, isn't it? 28, and because of the negative charge, you have 1. So altogether 35, right? Not 36, right? 36 here. Altogether 36 electrons. 36 electrons. Iodine is the center. Chlorine, 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 chlorine. 1, 2, 3, 4. Deduct out of 36 divided by 2 is 18. 18 minus 4 is 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now extra negative charge. So square plane means 90 degrees. Right, okay. So third one is done. Fourth one, electronegativity of the nitrogen atom. NH3. What is the next one? NH4 plus. And then NO2 plus. So NH3, all are nitrogens, right? All are nitrogens. Nitrogen is, what is that? sp3 hybridized. This nitrogen is also sp3 hybridized. This nitrogen, double bond oxygen, positive. That is also is sp. So I think sp is the most electronegative. So NO2 is the most NO2 plus is the most electronegative. sp3, this has a +1 charge. This has 0 charge. So therefore NH4 plus is the next one. And the last one is NH3. That is how the electronegativity vary. Is it okay if we draw the Lewis structure by completing the octet? Yes, completing the octet. Yes. Yeah. Doesn't matter, right? Doesn't matter how you get the structure, right? what you want is, you want to get the right answer, right? Why NH4 becomes before ammonia? Because this has a +1 charge. So electronegativity, these are the ones that we consider. This is the order. First one is the atom. If the atom is the same, hybridization. If the hybridization is the same charge, if the charge is the same, oxidation number. If the oxidation number is also the same, then other atoms. This is the sequence. So atom is nitrogen, nitrogen. But if you look at the hybridization, this is sp3, sp3. Then you have to look at the charge. Here you have a positive charge on nitrogen and here neutral charge on nitrogen. So that is why NH4 becomes earlier than NH3. Is it clear? Everybody okay with that? Right, okay, right. So let us look at part B. That's the rule here. Right, okay. Part B, let's work out that, right? See whether we can understand that. CN2O2H2 is a dibasic weak acid. It forms an anion with -2 charge on in the basic medium. Skeleton of the negative ion is given below, right? You have been given oxygen here, nitrogen here, then you have a carbon, then you have a nitrogen, then you have oxygen, right? Draw the stable Lewis structure for CN2O2 2-. How do you do that, right? Usual technique is this. You look at carbon, 4 electrons. Nitrogen, how many electrons? Nitrogen, 5 electrons, altogether 10 electrons. Oxygen, how many electrons? 6 electrons, 12 electrons. Because of the negative charge, you have another extra 2 electrons. So 10, 12, 22, 23, 24 plus 4, 28. 28 divided by 2 is equal to 14 electrons, right? 14 pairs. 1, 2, 3, 4. 4 pairs are drawn now. So that means you need to include another 10 pairs. So how do you place these 10 pairs? You place these 10 pairs based on this, right? 10 pairs you based on that. 10 pairs you start from the most electronegative element. So 1, 2, 3, 4, 5, 6, right? And then look at the nitrogen, 7, 8, 9, 10. There you have 10 pairs are placed. Let us look at the charges here. Charges is 1, 2, 3, 4, 5, 6, 7. 7 means -1. Nitrogen 1, 2, 3, 4, 5, 6. That means +1, isn't it? Carbon, what is the charge? +2. Nitrogen +1. Oxygen -1. So where do you neutralize the charges? Neutralize the charges by bringing these electrons to carbon. Bringing these electrons to carbon. Right? So what is the answer here? You get this thing here. And then let us say duplicate this. Right? So this is your answer here. Well, let us erase some of these things. So that is gone. That is gone. So what you do is we make a double bond here. Make a double bond here. Make a double bond here. Right? I think that is okay now. These are removed. Did you understand that? Nitrogen should negative. No, what is what? Nitrogen negative. Right, yes, negative. It should be negative. Yeah, you are right, Yes, my bad. It should be negative one, not positive. Negative. Negative here, negative here. That is why the electrons are gone to that. right? So you get this kind of answer. Draw the most stable. Draw 3 resonance structures for this one. So how do you draw resonance structures for this? So this is how you work on the resonance structures, right? So how do you do that? You can remove the electrons from here and then remove the electrons from there also. So you get oxygen, double bond oxygen, nitrogen, and then you have a carbon, double bond nitrogen, and there is this oxygen. 1, 2, 3, 4, 5, 6 negative. This is the lone pair. This lone pair is still there. 1, 2, 3, 4. And you end up with a carbon with a negative charge here. That is one resonance structure that you can think of. What is the other resonance structure? Other resonance structure is this one, where you can push the electrons here and break the green arrow there, right? So that one is oxygen, nitrogen here, single carbon. This is, right? So I will erase this, otherwise you will confuse. This arrow we are going to erase, this arrow we are going to erase, right? So nitrogen, triple bond here, carbon, single bond nitrogen, and then oxygen. 1, 2, 3, 4, 5, 6 negative. 1, 2, 3, 4, that is also negative. And then this goes into that will give you a positive charge. And this will give you a negative charge. Clear? You can come up with another resonance structure thinking that these electrons are given to that. No, not that electron. We'll take this molecule. Take this molecule again. And we'll do a different one, right? So I'm going to erase this. We are going to erase this. So now the electrons can be pushed from this side to this one. Electrons can be pushed from this side to this one. So when that happens, you get oxygen, nitrogen, carbon, triple bond nitrogen, and then this is oxygen. 1, 2, 3, 4, 5, 6 negative. This is positive. That carbon has no charge, extra charge here, negative, and this one is always negative. So these are like the resonance structures, but you can come up with other resonance structures as well. Can we also draw unstable resonance structures like the one having positive charge on nitrogen? You can, yes, you can. These are resonance structures. No? They don't say, don't draw unstable resonance structure. There's nothing like that. Draw 3 resonance structures. You can write any resonance structure as long as it is adhere with the rules that is there, right? These are few resonance structures that you can draw. Then the third one is draw a rough sketch of this one showing approximate bond angles, right? Okay. So what I'm going to do is I will copy this again, paste it, right? This one, this is our stable structure. So we will copy that again and we'll paste it and we'll try to decide on the bond angles. Look at this one, right? I want you to pay attention. But don't lose your focus, right? Okay, so I will erase this, I will erase this one. Can you tell me what are the bond angles there? So between this and this, what is the bond angle? This is sp2 hybridized. This is also sp2 hybridized. What is the bond angle? Right? So 120 degrees, you need to deduct 2 degrees for a long pair. Like what you get is 118 degrees here. This is also 118 degrees here. Would you agree with that? 118. So based on that, right? Based on that, there are no hydrogen hydrogens are also there, yes. Yeah, because it's not the anion, it's the hydrogen. Yes, I'll mark that hydrogen as well, right? So these ones will have an angle of what? 100. What is the angle? 109.5 because of the two lone pairs that is present. It has an angle of 105.5, roughly equal to 105.5 angles. Agree with that? මොකද කියන්නේ? It says H2CN2O2, right? So let us draw the structure, right? I'm deciding on a color here, right? See whether we can work it out. Nitrogen, double bond carbon, double bond nitrogen, right? And then you have a angle like this, angle like that. Then you have oxygen and the angle like this, where you have a lone pair, where you have a lone pair. Oxygen and an angle like that, where you have a lone pair, where you have a lone pair. There's a lone pair here, there's a lone pair here. Check whether you got that answer there. So this is your lone pair, this is the lone pair, this is the lone pair, this is the lone pair, this is a lone pair as well, this is the lone pair as well. බලන්න හරිද කියලා? So your angles are like this. This one is, what is the angle? 105.5. What is this bond angle? 120 less than that. 120. So not 120, less than that, 118 I said. 118. This is 118 as well. This is 105.5. And don't forget the hydrogen here. There's a hydrogen as well. Is it clear? Did you understand that? Everybody? Right. So you can come up with different angles. You don't have to trace it in the symmetric manner. You can turn in this manner also, right? OH in the opposite manner as well, not only on the same manner, right? So go to the next page, see whether we can work that out as well. Part C, complete that. Complete the answer, right? Complete the given table based on the Lewis structure given below. So they have given NH2 with a lone pair, carbon, and then there's a NH2 again with a lone pair, double bond nitrogen with a lone pair, and then nitrogen, double bond oxygen, dative bond oxygen, plus and minus. So here you have a lone pair, here you have a lone pair as well, right? So the carbon numbers, this is carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4, and this is the oxygen number 5. And then they say VSCPR around the atoms. Likewise, they ask various things. N1, C2, N3, N4. So VSCPR pairs. Can you tell me what is the VSCPR pairs? VSCPR pairs. N1, right? N1, what is that? N1 VSCPR pairs are 4. C2, it is 3. N3, it is 1, 2, 3. N4, 1, 2, 3. Is it clear? Did you understand that? VSCPR pairs, right? Next one is electron pair geometry around the electron pair geometry. What can you say about the electron pair geometry? First one is 4 means electron pair geometry is tetrahedral. 3 means trigonal planar. 3 means again trigonal planar. N4, 3 means what is that? Trigonal planar. Okay, thank you for that typing. Very nice. Trigonal planar. Thank you. Right. Electron pair geometry is that. What is the next one? Shape around the atom. Shape. Can you tell me what are the shapes here? What are the shapes? First one, it's trigonal pyramid. So I will say trigonal pyramid. Because there's one lone pair, trigonal pyramid. C2 is trigonal planar, right? C2 is trigonal planar, right? Trigonal plane. Right, okay. What is the N3? N3 is bent geometry or angular. Angular. And N4 is trigonal planar. Trigonal planar. Right. You guys are good at this, huh? Very good. Oxidation number. Oxidation number. N1 carbon is nitrogen is all -3, I think. Right? C2, what is C2? Nitrogen, that is +4. Yes. Nitrogen is negative. For each nitrogen, it is negative when you are breaking a bond. If it is a pi bond, you give -2 to nitrogen, +2 to carbon. N3, what is the N3? Nitrogen on this side. This side is -2. Yes, -2. N4, what is the answer? N4, you get plus. Which one is that? +4, right? Because there's a positive charge on nitrogen also. No? So it is +4. Is it clear? +4 is the answer. Not +5 because on the other side there is a nitrogen. Right? Oxidation numbers are like that. Identify atomic hybrid orbitals involved in the formation of the sigma bond on the Lewis dot dash structure. N1C2. Right? N1C2. Yes. N1C2 because it's a dative bond. So what is that? N1C2. N1 is sp3. C2 is sp2. sp3, sp2. C2N3. What is C2N3? C2 is sp2 and N3 is sp2. Agree with that? N3, N4. N3 is sp2. N4 is sp2 as well. N4O5. N4O5. N4 is sp2. The other one is 2p. Or you can say sp2O5 because it's a terminal one. People consider it as non-hybridized. N1H. What is N1H? N1H. Okay, so that is sp3 and on the other side it is 1s. Agree with that? Right. Identify the atomic orbitals involved in the formation of the pi bonds in the Lewis dot dash structure. Diagram in part 1. C2N3. Right. So that is, what is that? C2N3 is 2p and this is also 2p. N4O5. N4O5. 2p and this is also 2p. Agree? Did you understand that? Right? Yeah, okay. So because terminal atoms, people consider it as non-hybridized. You can say sp2, but it is also considered as non-hybridized. Right? All correct, send the second paper. Okay, that I'm glad to hear that. See, you're like, everything will work out. That is how it falls into one place. Can you explain 1s and 2p again? 1s and 2p means, there's hydrogen here. There's hydrogen. Hydrogen comes with 1s orbital. This is, it's a terminal atom. So terminal atoms, we consider it as non-hybridized. The hybridization has not taken place. For O5, there is a double bond, so can't we say that there is a sp, there is a sp3, sp2. sp2 is okay, yes, you can say sp2, right? In the exam, it is given for both of them. Like, even if you write 2p, they consider it as right, and for sp2, 2p, both are okay. How can N1 has +3 oxidation state? N1, so let me take that picture, right? So we will take that part out. Right, so we'll place it here. So this is your N1. Let me erase some of these unnecessary things there. And then expand that structure. If I expand it, you get hydrogen here, hydrogen here. So what you need to do is you need to break the bonds. And giving negative charge for the negative charge for the more electronegative atom, right? So negative charge for the more electronegative atom, this is -1, this is +1. When you break it, this is -1, this is +1. When you break that, this is +1 and this is also -1. So here you get -3 oxidation state. Is it clear? Did I write +3? No, -3? Yes. N1, that is how you get the -3 oxidation state. Did you understand that? Right, okay. Can you explain how to check the oxidation number? Right, what you do is, let us take an atom, A and B, right? Others, you all can go, like, otherwise you will find it boring, right? You all can go. Thank you, right? Good night, take care, right? We'll meet again. So the answer to that is, how do you check the oxidation number? Let us say this is more electronegative, and this is less electronegative. This is less electronegative. You break it in such a manner that the electrons will end up in the more electronegative atom. So it will be like that. So A and then B. So whatever the charge that it accumulates, that is the oxidation number. Right? That is how the bond method is this. Is it clear? Everybody understood that? Right. Any other questions from the paper? Right. Okay. So what is it? Please explain 2p. Yeah. What do you mean by 2p? Which one? Which one? Question mark. What is that? Please explain 2p. Where? The last question now, okay. Last question, C2, N3, these are pi bonds, no? Pi bonds are with unhybridized orbitals. Unhybridized orbitals. Otherwise, they can't form a bond. So, in order to get this unhybridized orbital, what are the only unhybridized orbitals? These are 2p's. So, they will form 2p overlap, where you have a p orbital parallel and then p orbital parallel, where you get this overlap taking place, right? Like that. So that is 2p overlap. So this is called 2p Z, 2p Z, or 2py, 2py. It's a pi bond. So the pi bond is formed between 2p's. Clear? Right, okay. So like extra class is not tomorrow, right? not tomorrow, that will be on the POE day, like I told you. So I'll tell you, I'll send it in the group, the link and everything in the morning. I think I mentioned these things in the class. Neither. Right? Last time I mentioned I will start at 8 and we'll do 3 hours. Right? So I'll tell you. I'll send you the link and everything uh, through the website. Right? So not tomorrow, not day after tomorrow, that will be on the POE day. And then we need to think about having some extra classes while the A-level exam is going on. While you have school holidays, I want to do a little bit of solid work and then cover up some of those materials. Arid, I hope you are ready for that. Right? Oh, okay. Right. Thank you. Right. Okay. Good night. Good night. Ah, God bless you. Right. Thank you. Bye. Thank you. Bye.